Somewhere past the orbit of Neptune, the radio signals from a spacecraft begin to take more than 4 hours to complete a one-way trip to Earth. At this distance, space feels less like a landscape and more like an absolute continuum of silence. If a critical system fails on a crewed vessel traversing this region, the humans inside might still feel entirely alive, breathing warm air and watching steady telemetry on their screens. Yet physically, mathematically, their fate may already be sealed. The boundary of rescue in deep space is not a physical wall, nor is it marked by a sudden visual landmark. It is an invisible, shifting horizon determined by orbital mechanics, kinetic energy, and the relentless speed of light. Long before a ship reaches the edge of the solar system, it passes a subtle geometric threshold where no pursuing vessel, no matter how powerful, can ever catch up before life support expires. If you enjoy exploring the deep mechanisms of space and the silent physics of the cosmos, consider subscribing and joining us for these long-form journeys. When we imagine a spaceship stranded in deep space, our human intuition naturally envisions a search and rescue operation similar to those conducted on Earth. We picture a distress signal transmitted across the void, followed by mission control scrambling a high-speed pursuit vessel to intercept the disabled craft. But in orbital mechanics and deep space kinematics, this intuitive concept of rescue is a dangerous illusion. In the vast vacuum beyond planetary orbits, interception is governed not by spatial proximity or straight-line distance, but by non-linear state vectors, phase space geometry, and kinetic energy differentials. To understand why a rescue vessel cannot simply turn on its engines and charge straight toward a stranded ship, we must examine the concept of orbital state vectors. A spacecraft's position in space at any given second is defined by 6 parameters, 3 spatial coordinates defining its position along x, y, and z axes, and 3 velocity vector components defining its speed and direction of motion. In terrestrial travel, 2 vehicles at the same location moving in different directions can easily alter their steering angles to rendezvous. In deep space, however, 2 vessels separated by a relatively small distance but possessing divergent orbital state vectors require immense velocity change known as delta V to match orbits. Without matching both position and velocity simultaneously, a rendezvous is physically impossible. The fast-moving pursuit ship will simply streak past the stranded vessel at thousands of kilometers per hour. Furthermore, deep space trajectories do not exist in a static Euclidean grid. Every object travelling past Neptune moves along a conic section, an ellipse, a parabola, or a hyperbola sculpted by the gravitational pull of the Sun and the massive outer planets. When a vessel fires its main engines, it does not merely push itself forward, it expands its orbital ellipse, shifting its apopsis or boosting its hyperbolic excess velocity. If a ship suffers a catastrophic propulsion failure or navigational drift, its trajectory becomes fixed along an unyielding gravitational path. To rescue that vessel, a secondary ship launched from Earth or a lunar staging base cannot simply travel along the same path. It must execute a high-speed intercept trajectory, requiring vastly higher kinetic energy to catch up, slow down, and lock state vectors before the stranded crew's life support degrades. This creates a dynamic horizon known as the phase-space boundary of reachability. This boundary is not a static line drawn around the solar system like an international border. Instead, it is a constantly mutating, mathematical envelope that expands and contracts based on 4 variables: the stranded ship's current velocity vector, the launch time delay of the rescue vessel, the maximum delta V budget of the rescue propulsion system, and the strict operational lifespan of the disabled ship's life support systems. As time passes following an onboard emergency, the reachability envelope shrinks exponentially. There is a precise, mathematically determinable minute past which the volume of reachable phase space collapses to 0. Past this point of divergence, no physical force available to human engineering can force 2 trajectories to intersect in time. The reality of this trajectory divergence is governed by the laws of Hamiltonian mechanics, which dictate how physical systems evolve through phase space. When a spacecraft loses main engine control, its position vector begins to drift continuously relative to its intended mission corridor. On Earth, a lost vehicle eventually comes to a halt due to friction, remaining stationary until help arrives. In the friction-free vacuum of deep space, momentum is conserved indefinitely. The stranded ship continues accelerating along its hyperbolic curve away from the solar system at tens of kilometers per second. Every second that mission control deliberates or prepares a rescue craft, the spatial gap expands by tens of thousands of kilometers, and the energy required to bridge that gap climbs exponentially. Moreover, matching state vectors with a high-velocity runaway craft introduces severe deceleration penalties. A rescue vessel that burns massive amounts of fuel to achieve an ultra-high pursuit speed must possess an equal amount of propellant to decelerate upon arrival. If the pursuit ship consumes 80% of its delta-V budget simply closing the distance, it will arrive at the stranded craft moving at a relative speed of 20 kilometers per second with no fuel left to brake. Rather than a rescue, the maneuver results in a hypervelocity flyby, where the pursuit vessel flashes past the stranded astronauts in a fraction of a second, leaving both ships stranded on divergent, unrecoverable escape vectors into interstellar space. This fundamental kinematic constraint transforms how we must view deep space exploration safety. The boundary of safety is not determined by how far a ship is from Earth in astronomical units, but by whether its current state vector resides within the kinetic envelope of pursuit. A ship orbiting Mars might be safely within reach of emergency assets, while a ship only slightly further out moving on a high-eccentricity solar escape trajectory might cross the point of no return within hours of a main engine failure. Rescue in deep space is not a tactical option that can be improvised on demand. It is a strict mathematical equation where the variables are set in stone the moment a trajectory is locked. To visualize the geometric complexity of this reachability envelope, consider a three-dimensional manifold constructed in velocity space. The origin of this manifold represents the launch origin on Earth, while the stranded craft moves along an expanding vector, moving away from the coordinate center. As time advances, the sphere of accessible states for the pursuing craft expands at a rate determined by its maximum engine thrust. If the position of the stranded craft escapes the boundary of this expanding accessibility sphere before the two manifolds overlap, the mathematical intersection set becomes empty. No future maneuver, regardless of duration or timing, can re-establish geometric overlap. The geometric topology of space itself closes the door. Furthermore, state vector calculation in deep space is complicated by multibody gravitational perturbations. Past the orbit of Neptune, a vessel is not merely subject to the central gravitational pull of the Sun, it experiences minor, continuous gravitational pulls from Jupiter, Saturn, Uranus, Neptune, and thousands of massive trans-Neptunian objects TNOs. These minor perturbations cause the nonlinear differential equations of motion to exhibit chaos-like sensitivity to initial conditions. A microscopic trajectory calculation error of a few millimeters per second at launch compounds into millions of kilometers of trajectory deviation over a multi-month chase, requiring continuous, fuel-expensive trajectory correction maneuvers that rapidly drain the rescue craft's remaining delta-V budget. Additionally, state vector matching requires precise alignment of the orbital plane inclination. Spacecraft do not travel on a flat two-dimensional sheet. If a disabled ship experiences an asymmetric thruster explosion that kicks its trajectory 3 degrees out of the ecliptic plane, a pursuing craft must execute a costly plane change maneuver. In orbital mechanics, changing orbital inclination at high hyperbolic speeds requires enormous lateral velocity changes. Burning fuel to alter orbital inclination directly reduces the amount of propellant available for forward acceleration and final rendezvous deceleration. further shrinking the reachability envelope and pulling the point of no return much closer to Earth. Consider also the mathematical formulation of trajectory intersection manifolds using Lambert's orbital boundary problem. To transfer a pursuing vessel from Earth's position to a moving target position across a fixed transfer time, orbital mechanics utilizes Lambert's theorem, which solves for the required velocity vectors at both endpoints. As the transfer time window shrinks due to declining life support availability, Lambert's equation yields exponentially higher initial burn velocities. At a critical minimum threshold time, the required initial velocity reaches infinity, representing a mathematical singularity where no physical solution exists. The equations of celestial mechanics explicitly demonstrate that time and energy form an impassable mathematical wall. Moreover, the problem of trajectory interception is compounded by the orbital motion of Earth itself. Earth orbits the Sun at roughly 29.8 kilometers per second. If an emergency occurs when Earth is located on the opposite side of the Sun relative to the stranded ship's departure vector, a rescue craft launched from low Earth orbit must first overcome Earth's orbital momentum or burn immense propellant simply to align its initial trajectory toward the outer solar system. This astronomical geometry penalty adds months to the intercept timeline, effectively shrinking the rescue envelope before the pursuit ship even clears the Earth-Moon system. Ultimately, the physics of beyond-reach trajectories reveals a sobering cosmological principle. In deep space, gravity and inertia do not negotiate. Once a vessel's state vector drifts past the interception threshold of available delta V, the laws of classical mechanics transform space from a navigable territory into a one-way corridor. The crew may remain fully healthy, their life support functioning perfectly for months to come, yet their physical path has separated permanently from the rest of human civilization. They have entered a regime of movement where space itself ensures that no physical object launched after them can ever catch up. To comprehend why deep space rescue becomes physically impossible past a certain threshold, one must confront the single most brutal equation in astronautical engineering, Tsiolkovsky's rocket equation. Formulated by Russian scientist Konstantin Tsiolkovsky in 1897, the equation establishes the absolute relationship between a spacecraft's mass, its exhaust velocity, and the total velocity change or delta V it can achieve. The equation dictates that to gain speed, a rocket must expel mass in the form of high-velocity exhaust gas. But because that propellant mass must itself be accelerated by earlier burns, the relationship between required delta V and initial fuel mass is not linear, it is exponential. This mathematical reality is known throughout aerospace engineering as the tyranny of the rocket equation. In conventional space missions within low Earth orbit or the Earth-Moon system, delta V budgets are tightly calculated for planned maneuvers, orbital insertion, station keeping, and trans-Earth injection. Every kilogram of structure, scientific equipment, life support apparatus, and human crew requires an exponential mass of propellant at launch. For example, to place a single kilogram of payload into deep space using advanced chemical propulsion, a rocket must launch with 20 to 30 kilograms of fuel. If a mission requires a sudden, unbudgeted emergency maneuver, such as reversing direction or mounting a high-speed pursuit, the delta V requirements multiply drastically, demanding fuel loads that dwarf the mass of the spacecraft itself. When applied to a deep space rescue scenario, the tyranny of the rocket equation becomes an impassable engineering wall. Suppose a crewed exploration vessel travelling through the Kuiper Belt suffers a catastrophic failure of its primary navigational thrusters, causing it to lock onto a high-speed hyperbolic escape vector out of the solar system. To rescue this crew, ground control cannot simply send a duplicate ship on the same path, because the stranded ship has a head start of days or weeks. The rescue vessel must travel significantly faster than the stranded ship to close the spatial distance before the crew's consumables run out. Achieving this higher speed demands a massive initial acceleration burn, which consumes an enormous fraction of the rescue ship's fuel reserves. However, the problem is only half solved when the rescue ship reaches the stranded vessel. In space, matching location is useless without matching velocity. If the rescue vessel arrives at the target coordinates travelling at 50 km per second, while the stranded ship is moving at 30 km per second, the relative velocity between them is 20 km per second over 70,000 km per hour. To dock, transfer the crew, or attach a tow cable, the rescue vessel must execute a massive deceleration burn to zero out the relative speed. According to Tsiolkovsky's equation, this secondary burn requires an additional exponential mass of propellant that had to be carried all the way from Earth, heavying the ship during its initial acceleration phase. This double burn requirement creates an unsustainable exponential mass cascade. To carry the fuel needed for the final deceleration burn, the rescue vessel must be exponentially larger at launch. But to accelerate that massive fuel load up to pursuit velocity in the first place, the initial launch vehicle requires exponentially more fuel still. For high-speed pursuit missions past 30 or 40 astronomical units, the mass ratio of the rescue rocket quickly exceeds thousands to one. A rescue ship capable of intercepting a runaway Kuiper Belt vehicle within a 6-month window would require a launch mass greater than the combined mass of every super-heavy rocket ever built in human history. Even the transition from chemical propulsion to advanced nuclear thermal or nuclear electric ion propulsion does not eliminate this fundamental barrier. While ion thrusters achieve extremely high specific impulse-expelling xenon or argon ions at exhaust velocities 5 to 10 times higher than chemical combustion, their thrust-to-weight ratio is minuscule. An ion-propelled rescue craft can achieve vast total delta-v over years of continuous acceleration, but it cannot deliver the rapid, high-thrust bursts required to execute a fast catch-up intercept before life support expires. Conversely, high-thrust nuclear thermal engines offer greater instant acceleration, but their propellant mass requirements remain bound by exponential scaling laws. Furthermore, the structural mechanics of spacecraft hulls impose severe limits on maximum allowable acceleration. If engineers were to design an exotic fusion propulsion system capable of generating massive thrust with high exhaust velocity, accelerating a heavy rescue ship at 10 Gs to catch a stranded vessel would crush its internal life support systems, fracture structural bulkheads, and cause fatal biological trauma to any human crew aboard. The human body can tolerate sustained accelerations of only 3 to 4 Gs for limited periods. Therefore, even if infinite propellant were available, biological acceleration limits impose an absolute physical cap on how fast a pursuit vessel can close a spatial gap. Consider also the physical limits of propellant storage over multi-month pursuit timelines. Advanced high-thrust propulsion concepts often rely on cryogenic liquid hydrogen or liquid oxygen. In the deep space vacuum, despite multi-layer insulation and active cryocoolers, solar radiation and internal electronics produce boil-off. Over a 6-month pursuit phase, a significant fraction of the rescue ship's stored propellant boils off into space, reducing the available delta-v for the crucial braking burn. This thermodynamic fuel loss further degrades the rescue vessel's operational reach, pulling the non-intersecting boundary even closer to the inner solar system. In addition, fuel tank structural mass adds a relentless deadweight penalty. As propellant is consumed during the initial acceleration burn, the massive empty tank structures continue to add mass that must be accelerated and decelerated, unless jettisoned via complex staging protocols. Staged rocket designs can improve mass ratios, but staging past Neptune presents severe mechanical reliability risks. If a staging collar jams or fails to separate cleanly in the deep freeze of space, the unjettisoned tank structure locks the rescue craft into a lower delta-v trajectory, dooming both the rescue ship and the target crew to orbital drift. Furthermore, the engineering challenges of orbital propellant depot refueling at the edge of the solar system present immense infrastructure bottlenecks. To support deep space pursuit craft, Hypothetical mission architectures propose staging automated propellant depots in orbit around Neptune or Pluto. However, maintaining hundreds of tons of volatile cryogenic propellants in distant orbits requires continuous active refrigeration, orbital station keeping, and automated docking infrastructures that are themselves vulnerable to deep space degradation. If a propellant depot experiences a boil-off valve failure or micrometeoroid leak, the entire emergency refueling network collapses, stranding rescue assets on the launch pad. Moreover, the physics of nuclear fusion and antimatter propulsion concepts, often cited as the ultimate solution to delta-V limitations, introduce unyielding engineering constraints. Antimatter annihilation engines require storing positron or antiproton fuel within intense magnetic traps. A minor microsecond fluctuation in magnetic confinement fields results in instantaneous annihilation of the antimatter fuel against reactor walls, vaporizing the rescue ship in a high-energy gamma-ray explosion. Fusion rockets require massive magnetic coils and heavy laser ignition systems that drastically increase the dry structural mass of the craft, reinstating the exponential mass penalty under Tsiolkovsky's equation. Consider also the structural limits of propellant tank wall thickness under hyperpressurization. To deliver propellants to high-thrust nuclear engines at rapid flow rates, fuel tanks must be pressurized using high-pressure helium gas systems. Higher tank pressures demand thicker, heavier composite walls, adding dry structural mass that reduces overall delta-V capacity. Every safety margin added to structural walls to prevent tank rupture in flight reduces the rocket's ultimate velocity yield, further compressing the reachability horizon. Additionally, the physics of nozzle ablation and thermal dissipation limits engine burn duration. High-thrust engines operating at temperatures exceeding 3000 Kelvin erode their carbon-carbon or niobium nozzle liners during extended acceleration burns. If a rescue vessel is forced to burn its main engines continuously for hours to achieve intercept speeds, nozzle throat expansion degrades thrust efficiency and specific impulse mid-burn. The engine loses efficiency precisely when maximum acceleration is required, failing to deliver the calculated delta-V needed to catch the runaway craft. This thermodynamic and mechanical bottleneck establishes a clear delta-V budget horizon. Beyond a specific spatial distance and elapsed time window, the total delta-V required to execute a successful pursuit and rendezvous maneuver exceeds the upper theoretical limit of human propulsion technology. Once a stranded vessel crosses this dynamic delta-V threshold, it enters a regime of space where no ship built by human hands can carry enough kinetic energy to reach it, slow down, and return. The math of rocket mechanics closes the door to intervention long before the physical distance seems insurmountable to human eyes. Among all the physical constants that govern the universe, none is more absolute, nor more unforgiving to deep space operations than the speed of light in a vacuum denoted as c approximately 300,000 kilometers per second. In our daily lives on Earth, electromagnetic signals appear instantaneous. We make phone calls across continents, stream high-definition video in real time, and control remote aerial drones with millisecond latency. This optical illusion of immediacy has conditioned human culture to believe that communication is always instantaneous, regardless of location. But across the vast distances of deep space, the finite speed of light ceases to be an unnoticeable delay and transforms into an impassable barrier to human agency. When a spacecraft ventures past the orbit of Neptune into the Kuiper belt, it operates at distances exceeding 30 to 50 astronomical units from Earth. At 30 AU, a radio transmission traveling at the speed of light takes 4 hours and 10 minutes to cross the vacuum to NASA's Deep Space Network dishes in Goldstone, Madrid, and Canberra. If an onboard computer on the spacecraft detects a critical system failure and transmits an emergency telemetry alert, ground control on Earth does not receive that message until more than 4 hours after the event has occurred. By the time engineers on Earth assemble in the control room to review the diagnostic data, the physical situation aboard the spacecraft is already 4 hours old. This photonic latency creates a fundamental breakdown in interactive control loops known as the causal disconnect. On Earth or in low Earth orbit, mission control monitors thousands of telemetry channels per second. If a valve sticks, a power bus shorts out, or a cooling line loses pressure, automated ground software or flight controllers instantly issue override commands to isolate the fault. But at a distance of 40 AU, issuing a command from Earth takes another 4 hours to return to the ship. The total round-trip communication loop spans more than 8 hours. If a critical failure requires a decision within minutes, such as venting a thermal runaway battery or stabilizing a tumbling attitude control system, ground control is completely powerless to intervene. They are not observing live events. They are viewing cosmic paleontology, the history of a crisis that concluded hours ago. As a vessel travels deeper into the outer solar system and toward interstellar space, this light travel delay expands linearly with distance. At 100 AU, roughly double the distance of Pluto, the round-trip communication delay reaches nearly 28 hours. At 500 AU, deep within the inner Oort cloud, a single question and answer cycle takes nearly 6 full days. Under these conditions, real-time tactical conversation, joint decision-making, and ground-assisted emergency repair protocols cease to exist. Mission control is reduced to passive spectators, listening to the delayed echoes of a spacecraft that must solve its own crises or perish in silence. This photonic horizon creates a terrifying phenomenon known as the causality bubble. Every event that occurs aboard a deep space vessel generates an expanding sphere of information that travels outward at light speed. Ground control on Earth exists outside this causality bubble until the light front intersects Earth's position. Conversely, any command sent from Earth to assist the ship exists in a separate causality bubble, traveling outward toward the spacecraft. If the vessel is moving away from Earth while experiencing a cascading hardware failure, the time required for help, whether in the form of remote software patches or physical intervention vectors to reach the vessel, expands continuously. The ship is effectively isolated within its own temporal light cone, separated from the rest of humanity by the structure of space-time itself. Furthermore, the finite speed of light imposes absolute limits on remote navigation and hazard detection. Ground-based deep space radar systems cannot illuminate hazards around a vessel located 50 AU away. Even if Earth-based optical telescopes detect an unmapped cometary fragment or icy planetesimal along the spacecraft's flight path, transmitting a trajectory patch to steer the ship clear requires hours of transmission time. If the hazard is detected by the spacecraft's own forward-looking sensors only minutes before impact, the onboard guidance system must execute an evasion burn entirely autonomously. If the onboard system fails to calculate the burn correctly, ground control will not learn of the resulting collision until hours after the spacecraft has already been destroyed. The physics of electromagnetic signal degradation across photonic distances introduces additional severe data bottlenecks. As radio waves expand outward over billions of kilometers according to the inverse square law, their signal power drops dramatically. By the time a X-band or Ka-band radio signal from 60 AU reaches Earth's parabolic dishes, its power level is measured in fractions of an atom, trillions of times weaker than the signal from a digital watch battery. To extract readable telemetry from this faint whisper, deep space network antennas must integrate data over long time windows, reducing the achievable data bitrate to a mere trickle of a few hundred bits per second. Ground control receives not high-definition video or real-time diagnostic streams, but compressed, slow-scan data bursts, further obscuring the true physical state of the ship. Moreover, solar conjunction events periodically cut off electromagnetic communication entirely. When the sun passes directly between Earth and a deep space craft, the solar corona's dense plasma refracts, scatters, and corrupts radio transmissions. These communication blackouts can last for weeks at a time. If an onboard life support emergency occurs during a solar conjunction, no signal, no matter how urgent, can penetrate the solar noise wall. The vessel is rendered completely invisible and silent to Earth, operating in absolute electronic darkness. Consider also the phenomenon of relativistic Doppler shifting and frequency drift under thermal stress. If a disabled spacecraft is tumbling rapidly end over end, its high-gain directional antenna spins out of alignment with Earth, causing the transmitted radio carrier frequency to wobble and lose phase lock with ground receivers. Ground dish arrays must perform complex, slow-frequency sweeps across broad bandwidths to reacquire the fainter signal, adding hours of delay to telemetry reception. If the antenna gimbal freezes due to thermal cold soaking, directional signal transmission drops to zero, dropping the ship off mission control monitors entirely. Furthermore, optical laser communications, often proposed as a high-bandwidth alternative to radio waves, face severe alignment mechanics over light hours of distance. To transmit data via a laser beam across 50 AU, the spacecraft's pointing mechanism must aim the laser with sub-microradian accuracy toward the future position where Earth will be 4 hours later. If the spacecraft experiences a minor attitude control vibration or thruster glitch, the narrow laser beam sweeps across empty space, missing Earth's optical receivers entirely. Re-establishing laser handshakes over light-hour baselines requires automated scan patterns that can consume days of precious power reserves during an emergency. Additionally, interplanetary plasma turbulence induces signal dispersion and phase jitter across light-hour communication baselines. The heliospheric solar wind plasma density fluctuates continuously due to coronal mass ejections and solar sector boundary crossings. As radio signals pass through these turbulent plasma streams, differential phase delays scatter signal energy across adjacent frequency channels. Ground receivers must deploy heavy error-correcting algorithms that reduce effective bandwidth, forcing spacecraft to strip detailed sensor diagnostics down to rudimentary binary pulse codes during crises. Consider also the physical limits of ground receiver dish availability. Earth's deep space network is a shared global resource supporting dozens of active robotic missions across the solar system. If an emergency occurs on a distant crewed vessel while all 3 major DSN complexes are locked onto critical planetary insertion burns for other scientific probes, ground control faces scheduling conflicts and antenna repointing delays. Every minute spent slewing a massive 70-meter dish toward the target vessel's coordinates adds to the latency clock, further eroding the window for ground-assisted intervention. The psychological impact of this lightspeed wall on a human crew is profound. Human civilization has operated for centuries on the assumption of connected authority, the knowledge that when an individual faces extreme danger, they can broadcast a call for help and receive guidance from experts. In deep space, past the photonic threshold, astronauts experience the absolute severance of this tether. They realize that no matter how loudly they broadcast their distress, no human voice on Earth will hear their words until hours later, and no human answer can reach them until long after their immediate survival window has closed. The radio speaker does not bring live comfort. It delivers silence, reminding them that they exist outside the real-time boundary of human civilization. Ultimately, the speed of light is not merely a speed limit for physical objects. It is the fundamental speed of causality in the universe. It dictates that action and response cannot occur simultaneously across interstellar distances. Long before a ship reaches the physical boundary of interstellar space, it passes the point where ground-based intervention becomes impossible. The universe enforces an unyielding law past a certain spatial threshold. Every spacecraft is entirely on its own, locked inside a light cone where help from home is not just far away, but physically locked in the past. When space exploration missions operate near Earth or the Moon, mission safety relies heavily on a distributed cognitive network. A lunar crew does not solve complex propulsion anomalies or environmental control system failures in isolation. They are supported by hundreds of specialized engineers, flight controllers, biomedical experts, and supercomputers working in real time at mission control. This distributed cognitive model allows human spaceflight to manage immense technical complexity by offloading data analysis, diagnostic troubleshooting, and contingency planning to ground-based infrastructure. However, as a spacecraft travels deep into the outer solar system, the expanding communication delay systematically destroys this collaborative framework, forcing a transition from distributed intelligence to complete cognitive isolation. This cognitive transition is not merely a technical challenge, it represents a fundamental shift in human decision-making architecture under extreme stress. When communication latency exceeds several hours, the psychological link between the crew and ground control alters dramatically. A message sent to Earth describing a system failure cannot receive an answer for half a day. During this prolonged waiting period, the crew must manage their own anxiety, control operational panic, and resist the temptation to take hasty, unverified corrective actions. Conversely, they must also guard against dangerous passivity, waiting for advice from Earth that may arrive too late to prevent structural catastrophic failure. The human mind, unaccustomed to operating in a total communication vacuum during life-threatening crises, experiences intense psychological strain as the realization sets in that ground control is no longer a co-pilot, but a distant historian. Furthermore, cognitive isolation exposes the inherent limits of spacecraft autonomous systems. To mitigate the loss of real-time ground control, deep space exploration vessels are equipped with advanced onboard artificial intelligence and automated diagnostic software. These autonomous systems are designed to monitor thousands of telemetry channels, detect anomalies, and execute instant emergency reconfigurations, such as switching to backup power buses or isolating leaking fluid lines. However, machine learning algorithms and rule-based expert systems are fundamentally limited by their training sets. They excel at managing anticipated failure modes programmed by human engineers before launch, but struggle when confronted with novel, compound, or unpredicted failure cascades. When an unpredicted compound failure occurs, such as a simultaneous thermal control malfunction, an optical navigation sensor degradation caused by a micrometeoroid strike, the spacecraft's autonomous computer may reach an algorithmic deadlock. It may issue conflicting system priorities, or enter a safe mode state that preserves power but halts progress along the required flight path. At this point, the human crew must step in to override the computer and solve the novel engineering puzzle manually. But unlike engineers on Earth, who have access to detailed digital twin simulations, complete technical archives, and physical test beds, the crew possesses only their onboard tools, limited reference manuals, and their own cognitive bandwidth exhausted by sleep deprivation and environmental stress. This breakdown of interactive problem-solving creates a compounding error cascade. In high-stress engineering environments, human decision-making without external verification is highly susceptible to cognitive bias's confirmation bias, fixation on incorrect diagnostic hypotheses, and operational fatigue. On Earth, mission control acts as a critical cognitive filter, questioning assumptions, cross-checking calculations, and preventing flight crews from executing dangerous diagnostic steps. In deep space, isolated from this external validation, a minor diagnostic error made by a tired astronaut can trigger a secondary failure, transforming a manageable technical glitch into a fatal, irreversible system collapse. Moreover, cognitive isolation severely impairs long-term strategic mission management. Deep space survival requires continuous, precise recalculations of resource consumption rates, trajectory drift, and equipment wear over months and years. When equipment begins to degrade past its design specifications, deciding whether to risk running a degraded main engine or conserving fuel while drifting requires complex risk-benefit trade-offs. Without the analytical power of ground-based supercomputing clusters to model thousands of potential trajectory outcomes, the isolated crew must rely on simplified onboard models, increasing the probability of selecting a suboptimal path that leads to eventual vehicle loss. Additionally, group dynamics under prolonged communication isolation introduce insidious social friction within the crew. Suspended in a small habitat surrounded by lethal vacuum, with no external human contact for years, interpersonal tensions elevate. Differences in operational opinion regarding emergency procedures can fracture crew cohesion, leading to breakdowns in command structures. When ground control can no longer serve as an authoritative mediator due to multi-hour latencies, internal disputes over resource rationing or risky maneuvers must be resolved entirely within the small cabin. Operational paralysis or mutinous splits in decision-making can prove just as fatal as a mechanical reactor failure. Furthermore, long-term cognitive isolation alters sensory processing and psychological resilience. The human brain evolved in a sensory-rich terrestrial environment, constantly processing dynamic acoustic, visual, and gravitational inputs. Inside a deep space habitat, sensory inputs are reduced to monotonous hums of life support fans, fluorescent lighting, and grey metallic bulkheads. Prolonged exposure to this low sensory environment induces cognitive dulling, memory decay, and reduced executive function, the exact mental capacities required to diagnose complex engineering anomalies during emergency survival scenarios. Consider also the phenomenon of cognitive overload during compound alarm states. In a complex spacecraft, a major power bus failure triggers hundreds of secondary alarms across life support, thermal management, navigation, and payload systems simultaneously. On Earth, flight controllers are divided into specialized consoles: flight, systems, Capcom, guidance, each monitoring a single subsystem to prevent cognitive saturation. A crew of 4 or 5 astronauts in deep space faces the entire alarm cascade simultaneously. The sheer volume of telemetry alerts, flashing warning screens, and audible alarm horns overwhelms human working memory, impairing logical analysis and driving the crew toward panic-induced errors. Moreover, the psychological phenomenon of spatial detachment known in aerospace psychiatry as the solitudinous effect exacerbates cognitive decline. As the visual size of the sun shrinks and Earth vanishes from optical viewports, astronauts experience a profound sense of existential dislocation. The psychological brain struggles to process the concept that every human being, every city, and every historical memory exists on an invisible speck billions of kilometers behind them. This existential weight induces severe depressive episodes, apathy, and fatalistic resignation, undermining the biological drive to fight for survival during prolonged crisis operations. Consider also the psychological mechanism of shared cognitive reframing under severe temporal isolation. When human teams operate near Earth, cognitive errors are often corrected through external social reality. The continuous stream of feedback from flight controllers, family members, and mission managers in deep space. As the communication tether stretches to hours and days, the crew forms an isolated, closed social system. Internal groupthink intensifies. Diagnostic hypotheses that would be immediately questioned by mission control become unassailable internal truths within the small cabin. If the commander or lead engineer fixes upon a flawed diagnostic assumption such as believing a cooling telemetry drop is a sensor fault rather than an active fluid leak, the rest of the crew is highly likely to acquiesce, reinforcing the error until physical collapse occurs. Furthermore, cognitive isolation destroys the redundancy of human expertise. On Earth, if a rare spacecraft system fails, mission control can instantly consult the original design engineers who built the valve, wrote the software code, or tested the material alloys decades prior. In deep space, the crew's collective knowledge is strictly limited to their own training and memory. If a failure mode occurs that falls outside their specific engineering specialties, They must reverse engineer complex physical systems on the fly, experimenting with high-value hardware under extreme time constraints, where a single wiring mistake or improper torque setting destroys their only remaining chance of survival. Additionally, sleep architecture degradation under chronic circadian dislocation severely compromises problem-solving capability. Inside a deep space habitat without natural sunlight cycles, human sleep-wake rhythms drift off 24-hour baselines. Disrupted sleep architecture reduces REM phase duration, impairing memory consolidation and spatial reasoning. During an emergency requiring continuous 36-hour diagnostic troubleshooting, sleep-deprived astronauts exhibit reaction latencies and error rates equivalent to individuals under severe alcohol intoxication, rendering them incapable of executing delicate repair protocols. Ultimately, the emergence of cognitive isolation marks the psychological point of no return in deep space travel. Long before a ship runs out of oxygen or fuel, it crosses a boundary where human intellect aboard the vessel is stripped of its terrestrial support network. The spacecraft becomes a tiny, fragile island of human consciousness navigating an indifferent cosmic void, where every decision must be generated, executed, and owned by a handful of individuals entirely alone in the dark. Consider also the phenomenon of diagnostic fatigue during prolonged technical crises. In a terrestrial engineering facility, shift rotations ensure that flight controllers remain mentally sharp and rested. In deep space, a small crew facing a multi-day life support crisis must work continuously without sleep. As sleep deprivation accumulates past 48 hours, cognitive processing speed drops by 50%, spatial reasoning collapses, and the ability to detect subtle diagnostic anomalies vanishes. The crew becomes trapped in a state of operational exhaustion, unable to solve the very engineering problems that stand between them and cosmic drift. Part 5: Thermal Entropy and the Thermodynamic Point of No Return. Deep space is fundamentally a thermodynamic wasteland. Far from the warm radiation of the sun, the background temperature of the cosmic vacuum drops to approximately 2.7 Kelvin, just a fraction of a degree above absolute zero. In this brutal cryogenic environment, heat is not merely a comfortable environmental condition, it is the fundamental currency of physical existence. Every computer circuit, fluid line, mechanical actuator, and biological cell aboard a spacecraft requires a precise, tightly controlled thermal window to function. The moment a vessel enters deep space, it enters a continuous, unrelenting battle against thermal entropy, the universal physical law that dictates that heat will always flow from warm artificial systems into the freezing infinity of the void. To survive in this environment, deep spacecraft rely on internal thermal management systems powered by radioisotope thermoelectric generators, RTGs, or compact nuclear fission reactors. These power sources generate electricity and waste heat by harvesting the natural decay of plutonium-38, or the controlled fission of enriched uranium. This internal heat is carefully routed through fluid loops containing specialized coolants to warm critical components, propellant tanks to prevent liquid fuels from freezing solid, electronic bays to maintain semiconductor conductivity, and human habitats to sustain life. However, nuclear thermal sources are not permanent. Their heat output decays continuously according to fixed radioactive half-lives and physical material degradation. The thermodynamic point of no return occurs when a spacecraft's internal heat generation capacity drops below the minimum rate required to counteract passive radiative heat loss. Because heat transfer in a vacuum occurs via thermal radiation governed by the Stefan-Boltzmann law, where radiated energy scales with the fourth power of temperature, a warm spacecraft continuously glows in the infrared spectrum, bleeding calories into the 2.7 Kelvin abyss. If a primary thermal loop fails, or if nuclear fuel reserves decay past a critical threshold, the vessel begins to experience an irreversible thermal cascade. Temperatures inside the ship begin a steady, unstoppable decline toward cryogenic equilibrium. As internal temperatures drop, spacecraft materials undergo catastrophic physical phase changes and mechanical failures. Liquid propellants such as hydrazine or nitrogen tetroxide freeze solid inside fuel lines, expanding and rupturing titanium conduits. Synthetic rubber seals, O-rings, and electrical cable insulation become brittle and shatter under mechanical stress, causing catastrophic vacuum leaks and electrical short circuits. Semiconductor microchips experience severe carrier freeze-out, halting computational processing across flight computers. The physical infrastructure of the spacecraft literally freezes to death, transforming a sophisticated machine into a silent, rigid block of irradiated metal. For a human crew aboard a dying spacecraft, the thermodynamic decline is a slow, agonizingly predictable march toward biological extinction. As primary habitat heaters fail, the internal atmosphere cools rapidly. The crew must concentrate their remaining electrical power into tiny localized thermal survival zones, such as sealed emergency ascent modules or EVA suits. But individual battery reserves are finite. As body temperatures drop below 35 degrees Celsius, hypothermia sets in, impairing cognitive function, slowing reaction times, and inducing fatal cardiac arrhythmias. Long before the atmosphere becomes toxic or oxygen runs out, thermal entropy claims the crew, freezing their bodies into biological preservation alongside the silent hardware of their vessel. Consider also the phenomenon of thermal gradient stress across the spacecraft structure. While one side of the vessel radiates heat into the 2.7 Kelvin void, any side exposed to faint distant starlight or internal reactor plumbing experiences localized thermal expansion. This continuous, uneven thermal contraction and expansion across titanium trusses and carbon composite hulls induces microfracturing and structural warping over time. If thermal control loops fail entirely, structural welds snap under thermal shock, compromising habitat pressure integrity and accelerating the release of internal atmosphere into the vacuum. Furthermore, thermal decay permanently ruins electrical energy storage systems. Lithium-ion batteries and fuel cells rely on electrochemical reactions that slow down dramatically as temperatures drop toward freezing, below minus 20 degrees Celsius. Internal battery resistance spikes, preventing the discharge of stored electrical energy. Even if solar panels or backup generators remain structurally intact, cold-soaked battery banks become incapable of accepting or holding electrical charge. The ship's electrical grid collapses not from a lack of potential energy, but from the thermodynamic freezing of its chemical charge carriers. Additionally, heat pipes utilizing liquid ammonia or phase change working fluids experience freeze-up anomalies. In thermal control systems, heat pipes transport waste heat from electronics to external radiator panels via capillary action. If fluid flow rates drop or temperatures fall below the ammonia freezing point minus 77 degrees Celsius, the working fluid solidifies inside the porous capillary wicks. This blocks all passive heat transfer, causing localized thermal runaway in electronics bays, while the rest of the ship continues freezing solid, a paradoxical state where components burn out while bathed in cryogenic surroundings. Moreover, the physical properties of structural metals undergo a ductile to brittle transition under extreme cold. Steel, aluminum alloys, and titanium that exhibit high toughness at room temperature become glass-like and fragile at 70 Kelvin. Microscopic vibrations from lingering attitude control thrusters or internal pumps propagate through cold-soaked trusses as destructive stress waves, snapping structural supports and severing critical electrical harnesses. The spacecraft becomes structurally glassified, incapable of enduring even minor physical maneuvers. Consider also the degradation of phase change materials used in thermal energy storage units. Modern deep space vessels incorporate phase change thermal wax reservoirs to absorb excess heat during peak engine burns and re-radiate it during passive coast phases. In extreme cold, if internal temperatures fall below the material's solidification threshold for extended periods, the thermal wax undergoes irreversible microstructural separation and volume contraction. Upon attempt to remelt, the material develops internal voids and thermal hotspots, permanently destroying its heat storage capacity and accelerating the vessel's thermal decay. Furthermore, thermal entropy severely affects structural composite materials and bonding adhesives. Spacecraft hulls rely on carbon fiber reinforced polymers, CFRP bonded with high-performance epoxy resins, at cryogenic temperatures near absolute zero. The thermal expansion coefficients of carbon fibers and resin matrices diverge significantly. This differential contraction generates intense internal shear stresses at the microscopic level, causing microcracking across composite layers. Over time, these thermal microcracks propagate through pressure bulkheads, leading to slow, undetectable atmospheric microleaks that steadily drain the habitat's air supply into the vacuum. Additionally, cryogenic sublimation alters external surface optical coatings. Spacecraft utilize specialized multi-layer insulation MLI blankets composed of aluminized mylar or kapton to minimize thermal radiation. Exposure to extreme cold and cosmic UV radiation causes outer polymer layers to become embrittled and delaminate. As insulation blankets peel away under solar wind pressure, the ship's emissivity ratio changes, increasing radiative heat loss and accelerating the internal freezing timeline. Furthermore, thermal entropy creates an absolute, non-negotiable countdown clock for any potential rescue attempt. Even if a hypothetical pursuit ship possessed sufficient delta V and speed of light trajectory calculations to catch a stranded vessel, it must arrive before the stranded vessel's internal thermal infrastructure collapses past the point of recovery. Once a spacecraft's internal systems have frozen solid and structural conduits have ruptured due to ice expansion, docking with the vessel yields only a frozen ghost ship. Rewarming a frozen, cold-soaked spacecraft from the outside cannot restore shattered electronics, cracked propellant lines, or dead crew members. Ultimately, thermal entropy demonstrates that space is not merely empty geometric distance. It is an active thermodynamic sink that continuously extracts energy from artificial structures. The 2.7 Kelvin cosmic background radiation represents an absolute physical flaw that never stops pulling. A spacecraft in deep space is a temporary as fragile thermal anomaly, floating in an ocean of absolute cold. The moment its internal energy production falters, thermodynamics begins erasing the anomaly, steadily bringing the vessel back into thermal equilibrium with the cold, silent universe. Additionally, the extreme cold accelerates thermoelectric junction degradation in radioisotope generators. RTGs rely on thermocouples made of silicon germanium or bismuth telluride to convert radioactive decay heat into electrical voltage. Under chronic thermal shock and low temperature gradients, thermocouples experience microcracking and dopant migration across semiconductor junctions. Electrical power output decays faster than predicted by isotope half-lives alone, depriving environmental control systems of the vital watts needed to prevent total habitat freeze-out. To fully appreciate how deep space separates a vessel from the possibility of rescue, one must examine the transition from planetary gravity wells to the vast, open gravitational landscapes of interstellar space. Near Earth, spacecraft maneuver within a well-defined gravitational hierarchy. A satellite orbiting Earth is trapped inside Earth's sphere of influence, a region roughly 1 million kilometers in radius, where terrestrial gravity dominates over that of the Sun. Within this sphere of influence, closed elliptical orbits are stable, and orbital maneuvers can rely on familiar orbital mechanics, raising an apopsis, lowering a periapsis, or executing Hohmann transfer ellipses to rendezvous with target craft. However, as a spacecraft travels outward past Jupiter, Saturn, Uranus, and Neptune, the gravitational influence of individual planets shrinks relative to the vast background gravitational field of the Sun. Beyond Neptune at 30 astronomical units, the vessel leaves planetary spheres of influence entirely and enters the domain of heliocentric escape dynamics. Here, orbital velocities drop to a few kilometers per second, and the gravitational pull of the distant Sun becomes extremely weak. At these immense distances, a small increase in speed, a mere kilometer per second of additional velocity, is sufficient to transform a closed, bound elliptical orbit into an open, unbound hyperbolic escape trajectory. Crossing the threshold from a bound orbit to a hyperbolic escape trajectory represents a fundamental kinematic shift. On a bound elliptical trajectory, a spacecraft is gravitationally anchored to the solar system. Even if its main engine fails, it will eventually swing back toward periapsis near the inner planets after decades or centuries, offering a theoretical window for long-term recovery. But once a vessel achieves solar escape velocity crossing the local heliocentric escape horizon, it possesses kinetic energy greater than the Sun's gravitational potential energy. It is no longer bound to return. Its path becomes an open hyperbola that leads infinitely outward into the interstellar void. This transition drastically alters the mechanics of any potential pursuit mission. If a stranded vessel is on a hyperbolic escape trajectory, a rescue craft launched from the inner solar system cannot simply match its orbital period, because there is no orbital period to match. The rescue craft must achieve an even higher hyperbolic escape velocity, requiring enormous initial launch energy. Furthermore, as both ships move outward into regions of ever weaker solar gravity, the Sun's ability to bend their trajectories back toward each other vanishes completely. In interstellar space, gravitational lensing of flight paths disappears, motion becomes virtually rectilinear, and any initial velocity mismatch causes the spatial distance between pursuit ship and target to expand linearly and indefinitely. Moreover, crossing the heliopause into the local interstellar cloud introduces interstellar hydrodynamic drag and microgravitational perturbations from the galactic disk. While interstellar space is extremely sparse, containing only about one hydrogen atom per cubic centimeter, a spacecraft traveling at relativistic speeds encounters a continuous flux of interstellar gas and dust. This interaction generates minuscule but continuous drag forces that alter the ship's predicted trajectory over light years. Simultaneously, the combined gravitational pull of nearby star systems such as the Alpha Centauri triple system and the massive tidal forces of the Milky Way galaxy begin to dominate the ship's motion. Navigating a rescue pursuit across this gravitational watershed requires continuously recalculating galactic phase space vectors, where even minor gravitational anomalies pull the target craft past the reach of pursuit algorithms. Consider also the loss of gravity assist opportunities. Within the inner solar system, spacecraft routinely utilize planetary flybys slingshotting around Venus, Earth, Mars, or Jupiter to gain massive velocity boosts without expending propellant. These gravity assists allow lightweight pursuit vessels to achieve extraordinary speeds by stealing orbital energy from massive planets. But beyond Neptune, the planetary slingshot network terminates. There are no more gas giants to assist a pursuing ship. Once a rescue vessel passes the orbit of Neptune, it can no longer rely on planetary gravity to alter its course or boost its momentum. It must rely entirely on its own onboard fuel mass. The safety net of planetary orbital mechanics dissolves into the empty void. Furthermore, hyperbolic trajectories in deep space suffer from extreme sensitivity to initial burn vectors. A microradian error in thrust vector alignment during the final escape burn past Neptune results in a trajectory deviation of hundreds of millions of kilometers by the time the vessel reaches the Oort cloud. For a pursuing craft trying to intercept a runaway ship, tracking and adjusting for this expanding spatial deviation requires continuous, high-precision, astronomical observation and mid-course correction burns. As propellant reserves deplete with each correction burn, the pursuer's ability to execute the final rendezvous burn shrinks, effectively pulling the point of impossible rescue closer to the solar system boundary. Additionally, such chaotic multi-body dynamics near the Kuiper Belt present unmapped gravitational hazards. The Kuiper Belt and Oort cloud harbour millions of icy bodies ranging from small planetesimals to dwarf planets like Eris, Sedna, and Make. As a runaway spacecraft passes through these outer orbital shell structures, weak gravitational interactions with unseen massive bodies introduce chaotic orbital perturbations. In nonlinear dynamics, these perturbations cause exponential divergence of nearby trajectories, a phenomenon known as Lyapunov instability. Two spacecraft following nearly identical vectors will diverge by astronomical distances over long timescales, making long-range intercept trajectory calculation mathematically unpredictable. Moreover, the galactic tide exerts a subtle, relentless torque on deep space escape hyperbolas. The gravitational mass distribution of the Milky Way's galactic disk and central bulge creates a vertical galactic tidal field. For objects travelling past 50,000 astronomical units in the Oort cloud, this tidal field shifts orbital angular momentum, gradually warping hyperbolic trajectories out of the solar ecliptic plane. A rescue craft launched along the original departure corridor will find the target craft shifted into a completely different galactic inclination plane, requiring massive lateral delta V burns that drain pursuit capabilities. Consider also the mathematical divergence of orbital asymptote trajectories in interstellar space. On a hyperbolic trajectory, the spacecraft approaches a straight-line directional vector known as the hyperbolic asymptote. In the deep field beyond 60,000 astronomical units, the curvature of the trajectory drops to zero, and the vessel moves along a fixed asymptote vector, determined by its hyperbolic excess velocity vector. If two pursuing ships depart Earth with a microscopic difference in asymptote angle, the distance separating their asymptotes expands linearly with distance travelled. In interstellar space, this asymptote divergence separates pursuit vectors by millions of kilometres, eliminating the possibility of a late-stage orbital convergence. Additionally, the phenomenon of gravitational capture boundaries near foreign stellar systems limits rescue feasibility. As a runaway spacecraft drifts past the heliopause toward a neighbouring star system, it enters the foreign star's gravitational sphere of influence. If the rescue vessel arrives after the target craft has entered the foreign star's gravity well, the rescue ship must execute complex three-body orbital capture burns to match state vectors within the new gravitational system. The fuel mass required to transition between two independent stellar gravitational wells exceeds the mass budget of any single-stage pursuit craft, permanently locking the runaway vessel into its new interstellar drift path. Ultimately, crossing the solar escape horizon marks the physical transition from solar exploration to interstellar drift. The solar system's gravitational well, which acted as a protective sandbox keeping objects tethered near home, yields to the infinite expanse of the galactic disk. Once a vessel crosses this orbital dynamics watershed on an unpowered escape hyperbola, it is no longer travelling between destinations, it has become an independent interstellar body. Gravity will never pull it back home, and human engineering no longer possesses the planetary levers needed to redirect its journey. Consider also the mathematical formulation of hyperbolic asymptote divergence in three-body planetary systems. As a spacecraft leaves Neptune's gravitational sphere, its trajectory vector can be modelled as a perturbed Keplerian hyperbola. A minor velocity error at periapsis past Neptune compounds exponentially along the hyperbolic asymptote. By the time the vessel reaches 40 astronomical units, the spatial dispersion region expands to a volume larger than the orbit of Jupiter, rendering manual visual search operations by incoming pursuit craft geometrically impossible. While orbital mechanics and propulsion equations define the kinetic limits of deep space rescue, the ultimate unyielding countdown clock is set by human biology. A crewed spacecraft is a closed, artificial biosphere, a complex technological bubble engineered to maintain atmospheric pressure, supply oxygen, scrub carbon dioxide, recycle water, and provide thermal regulation for biological organisms that evolved under the protective umbrella of Earth's atmosphere. The moment a spacecraft suffers a primary power, propulsion, or structural failure in deep space, its remaining life support consumables transform into a strict, non-negotiable biological countdown clock. Human physiology operates within narrow, inflexible environmental windows. A human being requires approximately 0.84 kilograms of oxygen per day, consumes roughly 2.5 kilograms of water, and generates roughly 1.0 kilogram of carbon dioxide through metabolic respiration. In short-duration spaceflight near Earth, closed-loop environmental control and life support systems ECLSS recycle water from sweat and urine using advanced vapor compression distillation and recover oxygen from metabolic carbon dioxide using Sabatier reactors and electrolysis units. However, no mechanical recycling system achieves 100% efficiency. Systems experience trace gas leakage, mechanical seal wear, catalyst contamination, and parasitic power drain. Over multi-year deep space missions, consumable mass gradually decays. In a deep space emergency scenario, the life support countdown equation can be expressed as a linear function of remaining mass reserves divided by metabolic consumption rates. If a critical failure destroys primary ECLSS recycling units, forcing the crew to rely on non-renewable emergency oxygen tanks, lithium hydroxide CO2 scrubbing canisters, and stored water reserves, the biological lifespan of the crew becomes fixed. If the emergency reserves provide 30 days of breathable atmosphere, the absolute upper time limit for any rescue vessel to arrive, dock, and extract the crew is precisely 720 hours. This biological countdown intersects brutally with the kinetic constraints of pursuit trajectories. To mount a successful rescue, the total time elapsed from the moment of emergency notification, including mission control analysis, rescue ship launch preparation, initial acceleration burn, deep space transit, deceleration burn, and final orbital rendezvous must be less than or equal to the remaining operational lifespan of the disabled ship's life support systems. If the minimum physics-based transit time for a pursuit vessel to reach the disabled craft is 40 days, but the crew's oxygen reserves will be exhausted in 30 days, the biological threshold of survival has been crossed. The rescue mission is mathematically doomed before the pursuit vessel even ignites its engines. Furthermore, metabolic survival metrics degrade non-linearly long before absolute oxygen depletion occurs. As lithium hydroxide canisters saturate and carbon dioxide levels in the habitat atmosphere rise above 0.5% partial pressure, the crew experiences hypercapnia, a medical condition characterized by severe headaches, visual confusion, cognitive impairment, and respiratory distress. At 2% CO2 concentration, executive decision-making capabilities collapse. At 5%, loss of consciousness occurs. An impaired crew cannot execute manual docking procedures, operate emergency airlocks, or assist rescue personnel. Therefore, the effective operational lifespan of life support is significantly shorter than the theoretical limit of oxygen availability. Additionally, water recovery failures introduce rapid biological collapse timelines. While a human can survive for weeks without food, severe dehydration impairs renal function, blood pressure regulation, and cognitive processing within 72 hours. In the dry, low-humidity environment of a spacecraft cabin, fluid loss through respiration is accelerated if water recycling loops freeze or become contaminated with toxic glycol coolants. The crew's survival clock shrinks to a matter of days, far too fast for any deep space pursuit craft to bridge astronomical distances. Consider also the metabolic cost of environmental stress. During a deep space survival crisis, crew members experience elevated heart rates, hyperventilation, and acute psychological stress, increasing their per capita oxygen consumption and CO2 production by 30 to 50%. Cold cabin temperatures caused by power rationing force the body to burn additional calories and oxygen through shivering thermogenesis. This stress-induced metabolic surge accelerates the exhaustion of remaining life support consumables, rapidly pulling the biological survival threshold forward in time and shrinking the window for rescue intervention. Moreover, emergency atmospheric depressurization events create immediate catastrophic limits. If a micrometeoroid strike punctures a habitat module, active nitrogen and oxygen reserves must be dumped into the cabin to maintain partial pressure while the crew locates and patches the hull breach. Every depressurization cycle consumes finite compressed gas reserves. If hull damage exceeds the capacity of emergency pressure management systems, the crew must retreat into pressurized spacesuits or survival pods, reducing their operational life support window from months down to a few dozen hours. Furthermore, trace atmospheric contamination introduces toxic limits in sealed habitats. In a closed cabin, off-gassing from synthetic insulation, electronic circuit boards, and lubricants releases trace volatile organic compounds, VOCs such as benzene, formaldehyde, and carbon monoxide. Under normal operations, catalytic oxidation beds continuously filter these toxins. If thermal power loss halts trace contaminant burners, toxic gas concentrations accumulate to lethal levels within days, poisoning the crew long before oxygen reserves run dry. Consider also the biological hazard of radiation-induced acute sickness during solar particle events. In deep space, outside the magnetosphere, a sudden solar flare or coronal mass ejection floods the habitat with high-energy solar protons. If habitat shielding is compromised or emergency radiation storm shelters lose power, crew members absorb fatal radiation doses greater than 4 Gray. Acute radiation sickness causes bone marrow suppression, internal hemorrhaging, and rapid gastrointestinal collapse, destroying biological viability before any rescue craft can bridge the spatial gap. Additionally, biological waste management failure creates severe infectious hazards over extended survival timelines. Closed habitats rely on active microbial digesters and vacuum drying units to process human feces and organic waste. If power loss disables waste processing systems, anaerobic bacterial growth releases toxic hydrogen sulfide and methane gases into the cabin air while proliferating pathogenic bacteria. Microgravity waste contamination induces severe bacterial gastroenteritis and sepsis among the crew, degrading physical stamina and shortening the biological survival timeline. Consider also the physical limits of artificial gravity systems on long-term muscle and bone preservation. Crewed deep space vessels often utilize tethered rotating habitat modules to generate artificial gravity via centrifugal force. If an emergency forces the ship to spin down its rotating modules to conserve power or execute emergency burns, the crew is subjected to prolonged microgravity. Extended weightlessness induces rapid muscle atrophy, bone mineral density loss of 1.5% per month, and cardiovascular deconditioning. After 6 months in microgravity, astronauts suffer severe orthostatic intolerance and skeletal fragility, rendering them physically incapable of enduring high-G emergency extraction maneuvers when a rescue ship finally arrives. Ultimately, the mathematical threshold of biological survival represents the hardest wall in deep space rescue operations. Orbital mechanics may permit a pursuing ship to catch a target vessel after 2 years of high-speed transit, but if human biology expires after 6 months, the interception yields only a silent tomb. Human physiology cannot be paused, overclocked, or reprogrammed to tolerate a vacuum. In the vast, slow-moving arena of deep space, the rapid, fragile chemistry of human life is the ultimate limiting variable that defines where rescue becomes forever impossible. Furthermore, trace atmospheric pressure decay triggers altitude sickness and pulmonary edema long before complete vacuum exposure, In a slow leaking pressure hull, as cabin pressure drops below 60 kilopascals, partial oxygen pressure falls below biological thresholds. Crew members experience acute hypoxia, euphoric confusion, and loss of motor coordination. Without active pressure suit inflation, blood oxygen saturation plummets, rendering astronauts incapable of operating emergency seal patches or communicating with incoming rescue vessels. Additionally, psychological hyperarousal during atmospheric crises accelerates biological oxygen depletion. Under panic conditions, human heart rates surge past 140 beats per minute, doubling metabolic respiration rates. In a small emergency survival pod, panic-induced hyperventilation consumes emergency oxygen reserves at twice the calculated baseline rate, collapsing a predicted 24-hour survival window down to 12 hours. Human psychological fear actively shrinks the biological time frame available for deep space rescue. When considering high-speed rescue operations across vast interstellar distances, mind-bending relativistic effects begin to emerge that further restrict the feasibility of intervention. In theoretical astronautics, when propulsion systems advance beyond chemical and nuclear thermal engines toward exotic relativistic concepts, such as antimatter annihilation rockets, beamed laser sail pursuers, or magnetic fusion torch ships, pursuit speeds can theoretically reach a significant fraction of the speed of light, denoted as relativistic velocities 0.1 c to 0.1 cm. However, accelerating a pursuing spacecraft to these extreme velocities does not eliminate the boundaries of rescue. Instead, it introduces severe relativistic phenomena governed by Einstein's special theory of relativity that create a new wall of physical impossibility. The first major relativistic constraint involves velocity addition and Lorentz transformations in classical Newtonian mechanics. If a stranded ship is moving away from Earth at 10% of the speed of light, and a rescue ship is launched from Earth at 20% of the speed of light, 0.2 c, we intuitively calculate the closing speed as simply the difference between the two velocities, 0.2 c, 0.6. However, at high relativistic fractions, velocity addition is nonlinear and governed by the Lorentz transformation equation. As velocities approach the speed of light, the relative closing speed between the two vessels is smaller than Newtonian mechanics predicts. Closing a spatial gap requires far more energy and time than classical intuition suggests, reducing the effective reach of high-speed pursuit systems. Furthermore, relativistic time dilation creates an extraordinary temporal asymmetry between the stranded crew, pursuing rescue crew, and mission control on Earth. According to special relativity, as a pursuing spacecraft accelerates to a high fraction of light speed, time inside the pursuit vessel slows down relative to Earth and relative to the slower-moving stranded ship for every day experienced by the crew aboard the ultra-fast rescue craft. Several days or weeks may pass for the stranded crew drifting at lower velocities. This means that while the rescue crew perceives themselves as traveling across deep space in a compressed time frame, the stranded crew's biological clock continues to tick at normal rates, accelerating their life support depletion relative to the pursuer's journey. Consider also the brutal biological and structural limits imposed by relativistic acceleration. To reach 50% of the speed of light quickly enough to intercept a distant runaway craft before its life support expires, a rescue ship must undergo sustained high-G acceleration over weeks or months. Human biology can tolerate a maximum sustained acceleration of roughly 3 to 4 Gs before retinal hemorrhage, blackouts, and structural circulatory failure occur, accelerating at a constant 1 G, 9.1 meters per second squared, which provides a comfortable Earth-like artificial gravity environment, requires nearly a full year of continuous acceleration to reach roughly 70% of the speed of light. If the stranded crew's survival window is measured in months, an accelerating relativistic rescue craft cannot gain sufficient speed in time without crushing its crew under fatal G-forces. Additionally, at relativistic velocities, The interstellar medium transforms from a benign vacuum into a lethal radiation hazard. Interstellar space is populated by neutral hydrogen atoms, dust grains, and micrometeoroids. To a spacecraft travelling at 30% of the speed of light, 90,000 kilometers per second, a solitary hydrogen atom becomes a high-energy ionizing proton beam capable of penetrating titanium hulls and damaging biological DNA. Dust grains measuring less than a millimeter in diameter strike the forward hull with the kinetic energy of heavy artillery shells, triggering explosive impact vaporization. To survive this relativistic particle bombardment, a pursuit ship must carry massive forward radiation shields such as multi-meter-thick beryllium plates or active high-intensity magnetic deflectors, which drastically add mass to the vessel, compounding the rocket equation mass penalty and pulling the interception boundary closer to home. Moreover, the deceleration phase at relativistic speeds introduces severe kinetic energy dissipation challenges. To rendezvous with the stranded ship, the pursuing vessel must reverse its orientation and ignite its main engines to shed its massive relativistic kinetic energy. The kinetic energy of a relativistic spacecraft scales with the Lorentz factor gamma-1. Dumping this enormous kinetic energy via exhaust plasma or magnetic braking screens generates extreme thermal radiation and structural stresses that risk destroying the pursuit craft during the final braking maneuver. If the braking system fails or experiences thermal breakdown, the pursuer will flash past the stranded target at relativistic speeds, a fleeting shadow crossing the void, leaving both vessels lost in interstellar space. Furthermore, relativistic Doppler shifts severely corrupt real-time navigational tracking and target acquisition. As the pursuit craft accelerates toward relativistic speeds, light reflected or emitted from the target ship undergoes extreme blue shifting, while signals from Earth undergo red shifting into low-frequency radio bands. Optical guidance sensors aboard the pursuit ship experience relativistic aberration and optical distortion, where stars appear to cluster forward into a bright central cone of light, distorting star tracker coordinate grids. Navigating a high-speed intercept under severe relativistic aberration requires complex autonomous relativistic transformations. A microscopic algorithmic error 0.3 c causes the intercept vector to miss the target by millions of kilometers. Consider also the phenomenon of relativistic mass growth at extreme fractions of light speed. As a spacecraft approaches the speed of light, its relativistic mass increases according to the Lorentz factor gamma. Accelerating a heavier relativistic mass requires exponentially more energy input from onboard reactors. This mass inflation effect diminishes the thrust acceleration efficiency of relativistic fusion or antimatter engines, enforcing a diminishing returns curve on pursuit speeds. The universe actively resists high-speed intervention by making objects heavier as they try to move faster. Moreover, relativistic beamed propulsion systems such as ground-based orbital laser arrays pushing a lightweight sailcraft suffer from beam dispersion over astronomical distances. A high-power laser array built on the Moon, or in Earth orbit, can focus coherent photon pressure on a light sail out to a few dozen astronomical units. But past 50 AU, diffraction laws cause the laser spot size to expand to millions of kilometers in diameter, reducing the radiation pressure on the sail to near zero. Once the laser beam diffuses, the pursuit sailcraft loses its acceleration source and coast on unpowered momentum, eliminating the possibility of high-speed late-stage trajectory corrections. Additionally, relativistic coordinate synchronization between moving reference frames introduces profound navigation paradoxes. In special relativity, simultaneity is relative. Events that occur simultaneously in Earth's reference frame do not occur simultaneously in the reference frame of the fast-moving pursuit ship or the drifting target. Determining the exact coordinate time when a rescue ship should execute its final deceleration burn requires synchronizing proper time intervals across 3 distinct relativistic reference frames. An uncorrected simultaneity error of a few seconds in proper time translates to an interception misdistance of hundreds of thousands of kilometers. Consider also the extreme magnetic braking requirements when utilizing interstellar magnetic scoops Bussard ramjets. Theoretical pursuit craft designs attempt to harvest interstellar hydrogen gas via massive magnetic funnels to feed onboard fusion reactors, eliminating the need to carry propellant mass. However, at relativistic speeds, the drag force generated by collecting interstellar ions exceeds the net thrust produced by the fusion reactor, a phenomenon known as the Bussard ramjet drag barrier. Rather than accelerating the pursuit craft, magnetic scoops act as massive electromagnetic brakes, capping the maximum pursuit velocity far below what is required to execute long-range deep space rescues. Additionally, relativistic time dilation causes severe clock desynchronization between onboard atomic clocks and Earth control clocks. Over a multi-month pursuit phase at 0 force C, cesium beam atomic clocks aboard the pursuit ship drift relative to Earth GPS baselines by several hours. If autonomous navigation algorithms rely on synchronized timestamps to calculate orbital phase angles, uncorrected relativistic clock drift introduces non-linear trajectory errors that pull the rendezvous vector off target. Ultimately, relativistic kinematics demonstrates that moving faster does not break the ultimate boundaries of spaceflight. It merely trades spatial distance for relativistic complexity, extreme radiation hazards, and biological acceleration bottlenecks. Relativity enforces a strict cosmic speed limit that cannot be bypassed by raw engine power. The universe ensures that beyond a certain phase space boundary, even a ship traveling near the speed of a light cannot catch a runaway vessel in time to save the lives aboard. Furthermore, the relativistic aberration of starlight distorts forward optical tracking during high-speed pursuit maneuvers. As a spacecraft accelerates toward relativistic fractions of light speed, stars in the forward hemisphere appear to shift position toward the direction of motion, concentrating into a bright central optical cone known as the headlight effect. This extreme optical distortion blinds forward-looking optical sensors, making it virtually impossible for high-speed pursuit craft to detect dark, non-emitting target hulls against the optical glare of aberration-concentrated starlight. As a spacecraft penetrates deeper into the outer solar system toward interstellar space, the physical connection between the vessel and Earth's Deep Space Network (DSN) systematically degrades until it breaks entirely. Near Earth, spacecraft rely on DSN's massive 70-meter parabolic dish antennas located in California, Spain, and Australia to send tracking signals, receive precise radiometric range data, and update orbital state vectors. Ground-based supercomputers process optical, radiometric, and Doppler tracking data to calculate course corrections with sub-meter precision. However, as distance expands past 50 to 100 astronomical units, radio signals weaken according to the inverse square law, signal-to-noise ratios collapse, and the physical tether to ground control dissolves into digital white noise. This breakdown of ground control linkage forces a mandatory transition from ground-guided navigation to fully autonomous onboard navigation. In the deep space void past Neptune, a spacecraft cannot wait for Earth to tell it where it is or where it is going. The vessel must become an independent, self-determining robotic entity capable of observing the cosmos, determining its own 6 degrees of freedom state vector, detecting internal anomalies, and executing trajectory correction maneuvers without human intervention from mission control. To achieve autonomous deep space navigation, the spacecraft relies on advanced optical star trackers, auto-nav algorithms, and pulsar navigation systems XNAV. XNAV utilizes onboard X-ray sensors to detect the highly stable, periodic electromagnetic pulses emitted by distant rotating neutron stars, or pulsars. By comparing the arrival times of pulsar pulses against an onboard atomic clock baseline, the spacecraft can triangulate its absolute three-dimensional position in interstellar space independently of Earth. However, XNAV systems require long integration times, heavy shielding, and precise cryogenic cooling to isolate detectors from thermal noise, adding significant mass and power overhead to the vessel's payload budget. Furthermore, autonomous trajectory management introduces severe algorithmic vulnerabilities when handling unpredicted failure modes. In conventional spaceflight, if a primary inertial measurement unit IMU experiences gyro drift or an optical sensor is blinded by a debris flash, human flight controllers analyze raw sensor logs, isolate the faulty sensor, and upload an algorithmic patch to restore stability. In autonomous deep space operations, onboard fault detection, isolation, and recovery FDR algorithms must perform this diagnostic loop automatically. If the onboard FDR software encounters an ambiguous sensor anomaly, such as simultaneous star tracker saturation caused by a nearby outgassing event, the autonomous system can enter an algorithmic deadlock or execute an incorrect thruster burn that alters the ship's course in a fatal direction. Consider also the phenomenon of cumulative sensor drift over multi-year timelines. Every accelerometer, laser ring, gyro, and optical sensor experiences microscopic mechanical drift and bias accumulation over time. Without periodic calibration against Earth-based radiometric tracking baselines, small measurement errors compound non-linearly. Over a 10-year journey through the Oort cloud, an uncorrected gyro drift of a few microarc seconds per day accumulates into an uncertainty ellipse spanning millions of kilometers. If a disabled vessel's autonomous navigation system experiences cumulative drift during an emergency phase, its reported position vector becomes unreliable, rendering any incoming pursuit craft effectively blind to its true location. Moreover, the loss of ground control severs the software update pipeline. Spacecraft software is not static. During long-duration missions, ground teams continuously write, test, and upload custom patches to work around degraded hardware components or optimize fuel usage. Once a vessel crosses the communication loss horizon, its onboard software stack becomes permanently locked. If an unforeseen hardware interaction occurs past this threshold, such as a software race condition in the life support controller or a memory corruption event caused by cosmic ray strikes, the spacecraft cannot receive a patch from Earth. It must rely on onboard self-healing software architectures, which are fundamentally limited by onboard memory and processing capacity. Additionally, autonomous navigation systems must manage complex and multi-objective decision trees under high uncertainty. In an emergency scenario such as a primary coolant leak accompanied by trajectory drift, the autonomous control computer must weigh competing operational priorities. Should it burn precious cold gas propellant to reorient solar panels, or thermal radiators toward optimal angles, or conserve propellant for an emergency return burn? When automated systems make a decision that prioritizes hardware survival over human crew comfort, such as shedding life support power to protect main engine computer memory, it can create a tragic conflict between human intentions and machine logic inside the isolated cabin. Consider also the threat of single-event upsets, SEUs, caused by galactic cosmic rays hitting onboard neural network hardware. Modern autonomous systems utilize radiation-hardened neuromorphic chips or deep learning accelerators to process high-dimensional optical navigation images. When a heavy cosmic ray nucleus pierces an AI accelerator chip, it can flip bit states in weight matrices, causing neural network classification errors. An autonomous navigation AI experiencing bit flip corruption may misidentify a distant background star as a target pulsar, executing a catastrophic course correction burn that sends the craft tumbling out of its mission corridor. Furthermore, autonomous decision-making algorithms suffer from the black box opacity problem. Complex deep learning models or high-dimensional optimization routines make trajectory decisions that human crew members cannot easily interpret or audit in real time. If the crew suspects the autonomous navigation system is executing an incorrect maneuver, overriding the AI requires manual reconfiguration of complex software parameters under extreme time pressure. A miscommunicated override between human crew and autonomous flight software can freeze navigation buses, dropping the vessel into an unrecoverable safe mode drift. Moreover, autonomous target acquisition during rendezvous maneuvers requires active lidar and optical tracking under low-light conditions. If the disabled target craft has lost power and cannot transmit an active radio beacon or illuminate its position lights, the pursuing autonomous craft must detect a cold, non-reflective hull against the black background of space. At distance, a dark spacecraft hull has an optical cross-section smaller than an asteroid fragment. If the pursuing AI fails to visually lock onto the target craft during the final high-speed approach window, it will miss the rendezvous entirely, flying past the silent target into the outer void. Additionally, autonomous propellant management software faces severe sensor calibration degradation under microgravity sloshing conditions. In low gravity, liquid propellant inside partially empty fuel tanks floats as chaotic, unpredictable liquid globules. Capacitive fuel sensors struggle to measure exact remaining fuel mass. If autonomous auto-nav algorithms miscalculate remaining delta V by even 5% due to propellant slosh measurement errors, the AI will execute an overly aggressive intercept burn, exhausting fuel reserves before the final rendezvous braking maneuver begins. Consider also the threat of optical sensor degradation caused by thruster plume contamination. Every trajectory correction burn fires attitude control, thrusters that expel unburned monomethylhydrazine or nitrogen tetroxide exhaust residues. Over years of operation, thin chemical films deposit onto forward star tracker lenses and optical auto-nav cameras. Contaminated optical lenses scatter incoming starlight, reducing star tracker sensitivity and introducing systematic astrometric position errors that degrade autonomous guidance accuracy during critical emergency maneuvers. Ultimately, the loss of ground control linkage transforms deep space exploration from a tethered expedition into an unguided interstellar voyage. When the radio link to Earth fades into background noise, the spacecraft leaves the protective digital umbrella of human civilization. The vessel becomes a solitary autonomous machine carrying human lives through an unmapped cosmic ocean, where a single uncorrected software anomaly or sensor drift can silently steer the ship past the point of no return into eternal, silent drift. Moreover, autonomous inertial measurement units suffer from subtle relativistic clock drift corruption. Onboard ring laser gyroscopes calculate rotation rates by measuring interference patterns between counter-propagating laser beams. Over multi-year deep space transits, continuous gravitational gradient changes and thermal fluctuations introduce micro-radian phase shifts in laser cavities. This uncorrected optical phase noise distorts the spacecraft's internal reference frame, causing autonomous trajectory calculators to execute unwanted thruster burns that steadily push the vessel further off course. Beyond the physical, mathematical, thermodynamic, and kinetic boundaries of deep space lies a profound philosophical and cosmological truth. The point in deep space where rescue becomes impossible is not merely an engineering limitation or a temporary threshold of current technology. It is a fundamental cosmological boundary defining the ultimate limits of human agency in the universe. When a spacecraft and its crew cross this dynamic phase space horizon, they transition from being members of a connected terrestrial civilization to becoming an independent, isolated cosmological artifact drifting endlessly through the Milky Way galaxy. As the vessel drifts deeper into the interstellar void, past 60,000 astronomical units, and into the vast uncharted space between star systems, the psychological and physical reality of its situation reaches absolute finality. The sun, which nurtured the evolution of human life for billions of years, has dissolved into an unremarkable star among billions of others in the galactic spiral arm. Earth is no longer a pale blue dot visible through optical viewports. It has faded completely beyond the resolution of the ship's finest sensors. The crew realizes that they have crossed a boundary from which no message, no physical force, and no human memory can ever pull them back. In this deep interstellar regime, the spacecraft enters a state of perpetual astronomical drift governed by galactic dynamics. Over timescales of millions of years, the silent vessel will complete vast orbits around this supermassive black hole at the center of the Milky Way galaxy, taking roughly 230 million years to complete a single galactic rotation, long after the human crew has passed away, long after their biological bodies have frozen into permanent thermodynamic preservation inside the sealed pressure hull. The structural shell of the spacecraft will remain a microscopic, engineered capsule of metal, silicon, and historical memory sailing through the cold cosmic night. Furthermore, the physical durability of a spacecraft in interstellar space is subject to ultra-long-term cosmic weathering processes over millions of years. Continuous bombardment by high-energy cosmic rays, interstellar dust grains, and micrometeoroids will slowly erode the vessel's exterior skin. Solar panel arrays will shatter, thermal blankets will degrade into microscopic fragments, and external communications antennas will snap under hypervelocity dust impacts. Yet, inside the heavily shielded interior bulkheads, delicate artifacts of human culture, digital archives, physical plaques, human remains, and structural blueprints may survive intact for eons, shielded by the absolute vacuum and freezing temperatures of deep space. This transforms the lost spacecraft into a cosmological time capsule, a silent monument to humanity's brief, ambitious attempt to reach across the stars. It joins a sparse population of derelict interstellar objects drifting between star systems, carrying the physical evidence of a technological civilization that once flourished on a small rocky planet orbiting a G-type star in the Orion Arm. If, in some distant epoch, millions of years in the future, another intelligent species or an advanced robotic descendant of humanity encounters this derelict hull in the interstellar void, they will discover a preserved snapshot of 21st century human engineering and biological fragility. Consider also the ultimate fate of human structural materials on cosmological timescales, over hundreds of millions of years. Quantum tunneling and spontaneous radioactive decay within structural titanium, aluminum, and carbon fiber hulls will slowly alter their atomic structures. Structural metals will undergo subtle crystal lattice degradation, while organic polymers decompose under continuous cosmic radiation. Yet, on macro scales, the geometric silhouette of the spacecraft, its aerodynamic nose cone, heat shields, and parabolic dishes will remain recognizable across galactic history. A tiny island of low entropy preserved in an expanding, high-entropy universe. Moreover, the philosophical implication of the deep space horizon reshapes human understanding of cosmic solitude. On Earth, human history is defined by interconnectedness, empires collapse, but survivors migrate, ships sink, but lifeboats rescue survivors, radio calls reach help across oceans. In deep space, the universe enforces a strict cosmic isolation principle. Past a certain boundary, human life is stripped of external intervention entirely. Consciousness is forced to confront the indifferent majesty of the cosmos in total self-reliance, realizing that existence is a fragile, temporary spark suspended in an unfeeling physical framework. Furthermore, the point of no return challenges humanity's hubristic assumption of cosmic dominance. We often view technological progress as a continuous linear curve that will eventually conquer every physical barrier, eradicating light-speed delays, mastering infinite propulsion energy, and trivializing vast interstellar distances. But the hard physics of deep space demonstrates that physical laws impose absolute limits on what technology can achieve. Thermodynamics, special relativity, Tsiolkovsky's rocket equation, and phase space geometry form an unyielding architecture that limits the reach of human engineering. Respecting these boundaries is not a defeat of human ambition, but the beginning of true cosmic maturity. Additionally, lost interstellar spacecraft contribute to the quiet archaeology of the galaxy. Just as terrestrial archaeologists uncover ancient shipwrecks on the ocean floor to understand Earth's maritime trade routes, future galactic civilizations may survey interstellar space to map the expansion boundaries of early technological species. Derelict exploration craft drifting past the Oort cloud mark the outer frontier limits reached by 21st century humanity monuments that record where our kinetic reach ended and cosmic silence began. Consider also the profound metaphysical symmetry between the birth of life on Earth and its preservation in deep space. Life on Earth originated in warm, wet tide pools powered by solar radiation and chemical gradients. In the deep space void, that same biological matter, preserved inside a cold titanium hull, becomes a durable seed of memory floating through galactic space. The spacecraft transforms from a tool of exploration into an immortal cosmic vessel, preserving the molecular signatures of Earth life across cosmic epochs. Moreover, the deep space horizon invites humanity to contemplate the true scale of galactic time. Human history spans a few thousand years, a mere tick of the cosmological clock. A lost spacecraft drifting through interstellar space for billions of years will outlive the sun itself. Red giant expansion will eventually engulf Earth and the inner terrestrial planets 4 billion years from now. But the distant derelict ship, coasting through interstellar space past 60,000 astronomical units, will escape solar destruction entirely. It will outlive its home planet, bearing silent witness to the fading of our star system long after Earth has been reduced to solar ash. Ultimately, the deep space point of no return serves as a powerful, humbling mirror for human civilization. It reminds us that despite our immense technological achievements, our supercomputers, our nuclear engines, our quantum sensors, and our global communication networks, the universe operates under absolute physical laws that cannot be rewritten by human will. The cosmos is not a benign playground designed for human comfort. It is a vast, indifferent expanse sculpted by thermodynamics, relativity, orbital mechanics, and the speed of light. To explore deep space is to accept this fundamental contract with the cosmos. It requires accepting that past a certain dynamic horizon, the safety net of Earth dissolves completely, leaving human explorers alone with the raw, unyielding physics of the universe. The point of impossible rescue is not a failure of engineering, but a cosmic boundary condition, a reminder that when consciousness steps out into the deep void, it must walk forward with eyes open, respecting the silent absolute laws that govern the stars. Additionally, the long-term survival of human biological remains inside derelict spacecraft presents a fascinating biocosmological phenomenon, sealed inside a sterile, frozen, pressurized module in the 2.7 Kelvin vacuum of interstellar space. Human cellular structures undergo near-perfect physical preservation. Shielded from solar UV radiation and atmospheric decomposition, biological DNA and cellular membranes remain structurally intact across millions of years, preserving the physical blueprint of 21st century human biology as a durable biological artifact sailing through galactic space.